Presentation today is regarding what we are offering before project construction. So first, maybe because now it's a very small assembly, so I don't know if you, regarding my first presentation, if you have any questions that needs to be raised, I can also answer these questions, or else I'll go directly to the presentation. So first, the outlines of the presentation. After a brief company introduction, I'll show you why is it important to reduce project uncertainties, how are we achieving this, and also how do we use LiDAR not after project construction but also before project construction as not only a replacement but mostly as a complement of the MetMast. So our mission in the industry can be divided in two parts. Before construction, we work closely with our clients at each and every stage of the project development in order to reduce project uncertainties, to come up with more bankable projects with higher financial returns. After construction, of course, there's no point of working on the uncertainties anymore because the project is already built. The only thing we can work on is on the project losses. So this was basically what I've presented before. So MeteoPole has four main activities. So we are providing our clients with a fully comprehensive wind resource assessment software package. I'll introduce this to I'll introduce it to you later. Bankable services also, no matter if it's independent third-party energy yield assessments, owner's engineer, lender engineer services. Pre-construction LiDAR services, so this will be also one of the focus of my presentation, and post-construction LiDAR services that we have already seen. So our clients, I've already introduced you to our clients. So the software package, as I said, like the software package that we have put up together is basically satisfying each and every requirement of a wind engineer throughout the project development. So from the very early stage of site selection, site prospection, site ranking, we can use the wind data generator, which is based on mesoscale modeling, in order to generate virtual MetMast data, wind maps, all the way through wind monitoring, during which we can use Windographer to do daily wind data monitoring, wind data analysis, etc., all the way to final microsighting, for which we use CFD technology from Zephy Tools. So for Windographer and Zephy Tools, it's pretty much solutions that are already existing. The wind data generator is a very new type of software because there's no other software capable of basically running automatic WRF calculation, automatic WRF mesoscale calculation. It has inbuilt global datasets, no need to download, and you get directly all the access to ERA, MERA, GFS, NCEP, CFSR data. So it's very important when it comes to, as an IPP, when it comes to project pipeline development, to have such a tool in-house where you can generate wind maps and have a very broad understanding of the wind resource through over very large areas. So, like, let's say, for example, you are interested in developing a wind farm in the state of AP, for example. You can just generate the entire wind map of AP using this software. If once you have generated this map, you can start going into a deeper analysis and start generating what we call virtual MetMast, so that you don't only understand what is the average wind speed, but you also understand what are the seasonal, monthly, diurnal wind variations. You can also create a grid of virtual MetMast to go to the next step, which is to start understanding even better the site potential before having any mass data, which is what we call the conceptual layouts and the virtual wind farms, where you can test, you can basically at the end base your decision-making process in terms of project implementation, mast installation, etc., not only based on wind speed numbers, but also on PLF, on tentative PLF, optimized capacity numbers. This is also a good way to understand how many masts would be required to monitor this wind site before starting monitoring, basically. So let's say, for example, by generating a virtual wind farm, you understand that the project potential is like 200 megawatts, so you would be more keen on investing in several mast towers rather than only one. So this is one of the illustration, which is an output of the WDG, directly exportable into Google Earth. This was done for the South Indian region. So now the focus of the presentation on reducing project uncertainties. So first, why are we focusing so much on reducing project uncertainties? What are now the WRA best practices? And how do we basically reduce all the uncertainties that are under control of the IPP and the project owner, which is basically the measurement uncertainties. So am I measuring the right wind speed? The annual variability, did the wind speed that I measure for this year, was it a high wind speed year or a low wind speed year when I measured? And also reducing the modeling uncertainties. So basically, when I go from my met mast to all my prospective turbine locations, is the model right or wrong? So first of all, why maximizing project bankability? It has become now a differentiating factors between all the different IPPs to start having very to bring certainty into their project, because there is a reduced access to credits. Also, because of the larger and larger investments due to the increased hub heights, the larger size of projects, it's very important to maximize your bankability. And most importantly, in the past 15 years, basically, we have a lot of reported cases of underperformance of operational wind farms. So why it's important to focus on uncertainties reduction? So I don't know if you are familiar with P75, P90, P50 numbers. I'll get back to this after, but basically, whenever you reduce your project uncertainties, it means that you will get a higher P75 and a higher P90. P75 and P90 are actually the numbers that will be used by all the financial institutions to assess the project financial viability. And higher is the P90, higher will be the debt equity ratio you can get from the lender. And basically, if you have a higher debt equity ratio, it means that you will have a higher return on investments. So now a brief introduction of what is P90, P75, P50. So usually what comes directly out of the resource assessment is the P50 number, and it's supposed to be the average value of the average production. And all the different scenarios are following a Gaussian distribution for which the average value is P50 and the standard deviation is the project uncertainties. So if you understand this, then you understand also that if you manage to control and actually reduce your project uncertainties for the same P50, you will manage to get a higher P75 and of course a higher P90. So this is what we are committed at. We are committed at reducing uncertainties in order to maximize this P90 to P50 ratio. So now the WRA best practices to achieve this. So first of all, at the very early stage of site selection and ranking, we can use a combination of mesoscale modeling plus CFD in order to identify high-value development opportunities before wind monitoring. So this is what I introduced already as virtual wind farms and conceptual layouts. Once we have identified the right sites, we can also use CFD even before having mass data to decide where is the best location to install the met masts in order to ensure mast representativity and to avoid anemometers, sensors, breakdowns, and maintenance. Of course, once you have decided where to locate your met mast, mast installation in compliance with IEC standard with calibrated class 1 anemometers is recommended if you want to ensure your data quality. Daily, once the mast is commissioned, daily wind monitoring and campaign management with maintenance SOPs and quarterly routine site visits to also ensure data quality and maximize your data recovery rates. LiDAR, we'll see this in the rest of the presentation. LiDAR, ground-based LiDAR can be used also as a complement to the met masts in order to reduce wind flow modeling uncertainties, not only the vertical, as we will see, like basically, if you don't have hub height measurements, we can use LiDAR to get you will always get Herbite measurements with a LiDAR. That's important to remember. And also the horizontal extrapolation uncertainty. So say you have a met mast and then there's a cluster of prospective turbine locations which is located far from the met mast. You only rely on the wind model. By using a LiDAR, even for a short, even during a short amount of time, you'll be basically reducing your horizontal modeling uncertainties significantly. So once you have completed your wind monitoring with high quality data, then you start running all the wind models, all the microsighting scenarios. And here, it's also important to understand that being an IPP, you have the right to decide on what is the best match between a given site, a given turbine technology, and a given site capacity. And this is basically also one of the new trends in the wind industry in India, and we hope it's going to remain like this as long as possible. Here, what we are also suggesting is to basically browse all the different scenarios of different site capacity scenarios, available machines, and have a decision-making table in the form of a PLF matrix, which will help you in understanding directly what is the best fit between your site, the turbine that you are considering, as well as the site capacity. Also, it's important as a wind resource engineer not to only focus on maximizing the power production. It's also interesting to also look at the cost of producing each and every unit of power. So this also can be it can be used as an index whenever you come to finalizing on the turbine, finalizing on the site capacity, etc., etc. So once you have monitored the site, run your model, decided on which turbine you're going to use, etc., then you can do the final assessments, the bank grade energy yield assessments on the selected final layouts with loss assessment in order to get from your gross values to your net values, and uncertainty assessments, which will help you to get from your P50 values to your P75 and P90 values. So the idea is to keep a consistent focus on maximizing the economic value of your sites. And this means that you need to keep optimizing both wind quantity by maximizing the P50 and wind quality by making sure that your turbines are IC site suitable. Also minimizing the cost of energy and reduce uncertainties at each and every stage of the project development, and earn confidence by bringing your P90 values as close as possible to your P50 values. So now let's see uncertainty by uncertainty, so measurement, annual variability, and wind modeling, how these three uncertainties are really under control of the IPPs. And basically, the sooner you start working and focusing on these uncertainties, the better it will be for the final assessments. So first of all, as I said, like even before having a met mast on site, you can start your analysis by running virtual wind farms in the form of pre-feasibility layouts, so that the decision making is based on capacity and PLF numbers rather than just on wind speed numbers. If the site is suitable, you will also be able to understand how many masts should be installed for these particular sites. And the idea is that this new trend in this wind resource assessments is that whenever you install a met mast, it's mostly to validate the resource rather than prospect for the resource. So this methodology is based on, as I said, coupling mesoscale modeling with CFD modeling, and this approach has been is now accepted by the International Scientific Committee. Mast siting. So why mast siting is important? It will bring whenever you put your met mast at one location, you want to ensure two things. You want to ensure that basically your met mast will be representative of the future wind turbines, and also that that you minimize the risk of breakdowns and maintenance of your sensors in order to maximize your data recovery rates. So here the idea is basically to focus only on the prevailing direction and to run CFD simulations in order to basically filter the best location by basically minimizing the horizontal deviation, minimizing the inflow angle, minimizing turbulence, and maximizing speed ups. So this is an illustration that has been done in one site in AP. So the prevailing wind was 270 degrees. The second prevailing direction was 90 degrees. And here we can see that basically at any height, we can use CFD to calculate the effect of the terrain, so not only the altitude, the contours, but also the roughness on the wind flow, and understand basically that where would be the best location to locate my met masts. So once we have decided where is the best location to the met mast, the next step is which sensors should I use. So of course we recommend to use appropriate anemometers, class 1 if it's complex sites, always calibrated using the MESNET procedure. Mast installation needs to be in compliance with the IEC standards in terms of boom length, boom orientation, clamp lengths, etc., etc. Flow distortion, so this is important to make sure that you correct the tower shading. So you have two kinds of met towers. One is a tubular tower and the other one is lattice tower. So when it comes to tubular tower, as you can see on this on this slide, you will have an acceleration on this part of the wind flow due to the tower effect and a deceleration in this parts. So this is why when you have a tubular tower, the IEC recommendation is to put your booms 45 degrees from the upcoming wind. And similarly, with a lattice tower, you will have, this time the acceleration, the deceleration will be at the same, but the acceleration will be located here. So this is why when you have a lattice tower, you should put your boom 90 degrees from the prevailing wind direction. And again, like by using all the technologies, like here is a windographer, you can directly identify the tower shading effect. Mast height is also very important because the vertical extrapolation is very uncertain. And the mast, your mast should be well equipped with multiple anemometers, multiple wind vanes, of course temperature, pressure, and humidity sensors for the air density, and a proper data logger. Campaign management also is very important to reduce measurement uncertainties. We recommend to have a very strong and proper documentation with mass commissioning report, site visit checklist, etc., etc. Daily wind data quality control with flagging rules, interaction with the field team to ensure maintenance is done within basically as soon as possible. Monthly campaign management reports and routine quarterly site visits, which means that basically it's not only, this was more related to what my colleague has presented, it's more like preventive maintenance rather than reactive maintenance. Now that we have seen how we manage to reduce all the measurement uncertainties, how do we manage to reduce the annual variability uncertainty? So as I said, like whenever you measure the wind on sites, you are always measuring for a short amount of time compared to the project duration. Let's say you measure for 2010, 2011, and at the end you realize that, okay, 2010 and 2011 was very high wind speed year compared to the long term, you will end up overestimating the project potential. Similarly, if you measure a low wind speed year, you will underestimate. So this is where reducing annual variability is very important. And this can be done basically by using what we call MCP methodology, which is measure, correlate, predict, where you use the on-site measurements along with mesoscale generated long-term data, and you put these two data sets together in order to understand what is the long-term adjustment that